Welcome to the deep dive. Today we're jumping into some really fascinating pure mathematics. We're looking at a puzzle from the legendary Paul Erdős, one that was solved only recently. It's all about something called rough numbers and prime gaps. And we're getting our insights straight from a really significant paper by Tao and Gaffney. So think of this as a quick guide to some cutting-edge number theory.
Absolutely. So to get started, we probably need to define a couple of key things. First, what's a prime gap?
Right.
Well, it's simply the space between two prime numbers that follow each other, like between 3 and 5. That gap, 3, 5, has a length of 2.
Okay, makes sense, like 7 and 11.
Exactly. The gap, 7, 11, that one has a length of 4. Now, the second idea is a rough number within one of these gaps.
Okay, rough number. What's that?
So an integer inside a prime gap is called rough if its smallest prime factor is at least as big as the length of the gap itself.
Okay, can you give an example?
Sure. Let's take that first gap, 3m5. The number inside is 4. Its smallest prime factor is 2. And the gap length is also 2. Since 2 is at least 2, yes, the number 4 is rough. So the gap 3 and 5 does contain a rough number.
Got it. And the other example? 7, 11.
Right. Gap length is 4. The numbers inside are 8, 9, 10.
Okay.
Smallest prime factor of 8 is 2. Smallest for 9 is 3. Smallest for 10 is 2.
And all those 2, 3, 2 are smaller than the gap length 4.
Precisely. So none of them are rough, according to the definition. That means the gap, 7 with 11, does not contain a rough number.
Okay, that distinction seems really important. And this seemingly simple idea actually caught Paul Erdős' attention.
It did. He thought about it quite a bit, and apparently he even changed his mind about what he expected to be true.
Oh, really?
Yeah. And he pointed out that gaps like 7, 11, where the primes differ by 4, sometimes called cousin primes, they never contain rough number.
Ah, because the number in the middle will always be odd, and the ones next to it divisible by 2.
Well, yes, and anything between p and p plus 4, like p plus 1, p plus 2, p plus 3, at least one must be divisible by 2 and one by 3. And since the gap length is 4...
Their smallest prime factors, 2 or 3, will always be less than 4.
Right, so cousin primes are sort of built-in counterexamples.
Exactly. They show it's possible for gaps not to have rough numbers. But despite finding these examples, Erdős eventually conjectured something else.
What was that?
He believed that even though these gaps exist, they become rare. Like, as you look at larger and larger primes, the proportion of gaps without rough numbers should actually shrink down towards 0.
So most gaps should have them, eventually.
That was his revised thinking, yes. And this became a known problem, hashtag 682, on Thomas Bloom's Erdős Problems website. It was out there for a while.
And now, finally, we have an answer thanks to Tao and Gaffney. So what did they find? Did Erdős get it right in the end?
He did. Their main result confirms Erdős's later intuition. Almost all prime gaps do contain a rough number.
Almost all, meaning the exceptions are rare. Very rare, yes. They showed that for primes up to some large number x, the count of these exceptional gaps, the ones without rough numbers, is significantly smaller than the total number of gaps. It's bounded by something like x divided by log squared x.
Okay, so they get rarer and rarer.
Precisely. And they actually did even better. If you assume another big conjecture in number theory is true, the Dixon-Hardy-Littlewood prime tuples conjecture, then they can pin down exactly how rare these exceptional gaps are. They found an asymptotic formula.
Wow. So like predicting the rate at which they disappear.
Sort of, yeah. They even estimate the constant involved around 2.8 something. It's quite specific.
That sounds incredibly deep. What kind of mathematical tools did they need to use to prove this? Must have been pretty advanced.
Oh, definitely. They used very powerful techniques from modern analytic number theory. Things like sophisticated sieve methods, think of them as advanced ways to count primes with certain properties. And also analyzing things called higher moments of rough number counts in short intervals. It's definitely not elementary stuff. It shows how far the field has come.
So the main question from Erdős is settled. But does this open up new questions? Or are there related things still unknown?
Oh, absolutely. While we know most gaps have rough numbers, the question of whether there are infinitely many gaps that fail to contain one, that's still open.
Ah, so even if they become rare, could there still be an endless supply of these exceptional gaps?
Exactly. And that question turns out to be related to other deep, unsolved problems about prime gaps, like Poulignac's conjecture, which is about whether every even number occurs infinitely often as a prime gap.
So it connects to even bigger mysteries.
It does. It shows that even when you solve one problem, it often points towards deeper structures and further questions about primes. Their nature is still quite enigmatic, especially concerning small gaps.
So wrapping this up for our listeners, what's the big takeaway here? We went from a sort of simple-sounding question about factors inside prime gaps
Right, a question posed decades ago.
to this really complex modern solution.
I think it really showcases the enduring power of mathematical questions. A conjecture from Erdős decades back can still fuel cutting-edge research today.
Yeah.
And the solution itself reveals these hidden structures and how prime numbers are distributed. It tells us something fundamental about their patterns.
It's a great example of mathematical progress. And maybe it leaves you wondering, how much complexity is lurking just beneath the surface of concepts we think are simple. What other long-standing mathematical puzzles might be nearing a solution right now?